Alright, in this video we're going to look at Green's theorem. Green's theorem says let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then Green's theorem says a line integral of some vector valued function over curve C is equal to the double integral over the region bounded by C of the partial of Q with respect to X minus the partial of P with respect to Y. And if we're doing a double integral over a region D, we're integrating with respect to the area of that region. If our line integral is written in differential form, it's the same thing. Remember, our line integrals can be written in this vector form or in differential form. And either way, the integral over some curve C is equal to the double integral over the region bounded by C of this expression right here. A couple reminders from the front part of the theorem. Positively oriented means as we travel around the curve, the region bounded should always be on our left. Okay, so if the curve is a simple circle, positively oriented means we would go around counterclockwise, because we would want the region inside the circle to always be on our left. Piecewise smooth means our curve is the union of finitely many smooth curves. Okay, so our curve doesn't necessarily have to be smooth, but we have to be able to write it as a union of smooth curves. Simple means the curve doesn't intersect itself anywhere between its endpoints. And closed means the initial point and terminal point are the same point. So our curve should start and stop at the same point, but not intersect itself anywhere in between. That is the kind of curve we have to have for us to apply Green's theorem. If the curve we're computing the line integral does not meet all of these criteria, then Green's theorem is not going to apply. So here's an example we're going to look at. Well, anyway, we've got a line integral of this function written in differential form, and our curve is one counterclockwise trip around a circle centered at 0, 0 with radius 4. If we were going to do this the old way, first we'd have to come up with parametrization for this circle, which we could use x equal 4 cosine t, y equal 4 sine t, and to make a trip around the circle, t would go from 0 to 2 pi. So those would be the parametric equations of my curve. And then I also would have to compute dx and dy because that's part of my line integral. Dx would be the derivative of this, which is negative 4 sine t dt, and dy would be the derivative of this, which would be 4 cosine t dt. So then I have to convert this entire expression to my parametric equations. So I'm going to replace x with 4 cosine t, I'm going to replace y with 4 sine t, I'm going to replace dx with this, and I'm going to do the same thing over here. So what we end up with is I can rewrite my line integral all in terms of the parametric equations, and I get all of this stuff. And my limits for the parameter t are 0 to 2 pi. If I simplify that a little bit, I get this integral, negative 64 cosine squared t times sine t plus 16 sine squared t plus 48 cosine squared t plus 16 sine t cosine t. And I would integrate all of this with respect to t, and I would evaluate from 0 to 2 pi. I will leave this for you to do as an exercise, and it's probably going to take you quite a long time because this is a tough one, okay? And if you do that, you should get 64 pi. I'll be honest, I used Mathematica and cheated a little bit. But anyway, if we do integrate this, this is something you can do. You just have to use some of your trig identities. You will get 64 pi. But the main focus of this video is to do this another way. Okay, the other way is to apply Green's theorem. C meets the criteria for Green's theorem. Counterclockwise trip around the circle means we're positively oriented, and it's definitely a simple closed curve. So according to Green's theorem, I can replace my line integral with a double integral of this expression here, and I'm going to integrate with respect to the area of the region inside the circle. So let's go ahead and try that. Okay, so here's my line integral written in differential form, and we're going to apply Green's theorem, and we're going to calculate this double integral over the region D. D is the region inside my circle of radius 4. Okay, and you're going to see that this makes things much, much easier for us. The partial derivative of q with respect to x, in this case, here's q. The partial derivative of q with respect to x is just 3. And this is p. The partial derivative of p with respect to y would be -1. So all I have here is the integral of 4 with respect to the area of region D. Now, because region D, we are inside a circle, it's probably going to simplify things if we polarize this one. So I'm going to convert my double integral to polar coordinates. So in polar coordinates, remember we have an extra factor of r, so this will become 4r dr d theta. And my circle has radius 4, and we want all the points inside that circle. So r is going to go from 0 to 4. And we have the entire circle, so theta goes from 0 to 2 pi. So my first step is the integral from 0 to 4 of 4r dr, which is just going to be 2r squared, and then r goes from 0 to 4. If I substitute 4, I get 32, and if I substitute 0, I get 0. So after my first integral, I'm left with just 32. So then my second step would be the integral from 0 to 2 pi of 32 with respect to theta, which would just be 32 theta. And then theta goes from 0 to 2 pi. And if I substitute 2 pi, I have 32 times 2 pi, which is 64 pi. Okay, if I substitute 0, I get 0. So notice, this is the same answer we got doing it the old way, but this, hopefully you see, is much, much, much easier. So there's definitely an advantage to applying Green's theorem in this situation. So here's another example we're going to take a look at. We're going to evaluate another line integral, and this one's also written in differential form. We have the line integral 2xy dx plus x squared plus 2x dy about the curve C, where C is actually made up of 2 parts, and it's the boundary of the region inside the ellipse, x squared over 9 plus y squared over 4 equals 1, and the circle, x squared plus y squared equals 1. Let's take a look at this. So in this example, we're dealing with the region between the ellipse and the circle. In other words, all the points outside the circle, yet inside the ellipse. If we're going to apply Green's theorem, we need to make sure we can represent the boundary of this region with a positively oriented curve. And the cool thing is, we can even do that if our region has a hole in it, as long as we do it carefully. So if we're going to go around the ellipse with positive orientation, that means we're going to go counterclockwise around the ellipse. Now, the question is, what do I do around the circle? Well, here's how we deal with regions that have a hole in them. We can start anywhere, really. If I'm walking around the curve this way, what I can do is introduce, let me do this in another color so you can see it a little bit better. I'm going to walk this way, and then I'm going to introduce a new curve that goes this way. And then I'm going to go around the circle this way. I'm going to come back this way and then finish around the ellipse this way. But remember, positive orientation means we have to keep the region on our left at all times. If I'm walking around the ellipse this way, the region is on my left. If I walk this way, part of the region is on my left. Now we have to make a decision, do I go around the circle this way or this way? Well, if I go around the circle this way, the region is actually on my right. If I go around the circle this way, notice the region we're talking about is always on your left. Then when I get back to this point, I can walk this way, part of the region is to my left, and then I continue around the ellipse this way. That entire trip around this curve, the region is on my left. So let me call this part of the trip C1. Let me call this C3, this C2, and this C4. I'm going to use C1 and C2 for the two curves that actually make up the boundary of my region. But I'm going to introduce curve 3 and curve 4 to make this a simple. So it turns out my boundary curve for this region is C1 plus C3 plus C2 plus C4. Okay? Now, the reason this works, if I'm going to do this integral, let me just call the integral for simplicity's sake. Let's just do it in vector form. And let's say I'm going to do the line integral over vector field f with respect to the length of the curve. So because C is the union of these four curves, I can say that my line integral is going to be the sum of these four line integrals. Okay, C2 FDR plus C4 FDR. Now the cool thing is the line integral over C3 and the line integral over C4, okay? These two curves have the same length. The only difference is we're going in the opposite direction. So whatever value I get when I find the integral over C3 is just going to be exactly the opposite of what I get when I integrate along curve C4. So these are actually going to cancel out. So I can say that my line integral over the curve that bounds this region is really just the line integral over C1 in this direction plus the line integral of C2 in this direction. Okay, so here's my line integral written in differential form, 2xy dx plus x squared plus 2x dy. And we're integrating over this curve, which as we talked about, we're going to comprise this curve of curve C1, which is a counterclockwise trip around the ellipse, plus C2, which is a clockwise trip around the circle. And because this curve meets all the requirements for Green's theorem, I can apply Green's theorem to this integral. So when I do that, I get, instead of the line integral over curve C, I've got the double integral over region D, which is just this region inside, of the partial of Q with respect to X minus the partial of P with respect to Y. And I'm integrating with respect to the area of this region. Okay, so in this example, the partial of Q with respect to X, here is Q. So the partial with respect to X would be 2x plus 2. And then I'm going to subtract the partial of P with respect to Y, which in this example would be 2x. So what I end up with is the double integral over region D of just 2. Okay, 2x minus 2x will be 0. Now, we can factor out the 2 because that's a constant. And we're left with the double integral of 1. Now, if you remember anything from last chapter, we know when we double integrate 1 with respect to the area of some region, that leaves me with what? Well, you're not here right now, so I'll answer for you. It's the area of this region. So what we end up with is 2 times the area of D. So when we apply Green's theorem to this problem, it turns out we don't have to do calculus at all. All we have to do is find 2 times the area of my region. Okay? So let me draw the region again, and let's do that. Again, my region is the region inside the ellipse which was x squared over 9 plus y squared over 4 equals 1, and outside the circle, which was x squared plus y squared equals 1. The area of this region, again, we're talking about this region, the area of this region would be the area of the ellipse minus the area of the circle, right? So if you remember, the area of an ellipse is pi times the major axis radius times the minor axis radius. The major axis is 3 units long, so it would be pi times 3, and the minor axis is 2 units long, so it's pi times 3 times 2. And the area of the circle is pi r squared, and in this example the radius is 1. So we end up with 6 pi minus 1 pi, which is 5 pi. And according to Green's theorem, I want 2 times the area of D, so 2 times 5 pi would give me a final answer of 10 pi. Okay. So it turns out that this line integral over C is just 10 pi. So Green's theorem can be used even if your region has a hole, as long as we can orient the curves in such a way that you can travel around keeping the region on your left at all times, which we can in this case.